Thank you very much for coming. Today we are going to talk about how we built Twine, a scalable drop-in real-time as a service that abstracts away the complexity of real-time communication and provides connection state recovery. My name is Maddy, and I'm here with Spencer, Chris, and Leeya, and together we built Twine. We are a distributed team of engineers coming from the different parts of the US and New Zealand. Here's a roadmap of what we're going to discuss today. We will start by defining what real-time is and the different ways it can be implemented. From there, we will zoom in on one way in particular, WebSockets. We will define what WebSockets are, their advantages, and their challenges. We will then discuss the current existing solution to these challenges and why we chose to build Twine. From there, we will discuss our journey of building Twine and some difficulties we encountered along the way. We will explain how a developer can use Twine in their existing application. And finally, we will wrap up with some future improvements that we would like to make to Twine. So let's get started. On the first slide, we describe Twine as a drop-in real-time as a service. But what is real-time and what type of applications use real-time? Real-time communication is a way of describing an exchange of information over a network at a speed that humans perceive as instantaneous. Specifically, data transmission of up to 100 milliseconds is categorized as real-time. This is because of the 250 milliseconds the average human requires to process and respond to a visual event. Real-time is used in many modern web applications. This includes collaboration applications such as Slack, video conferencing applications such as Zoom, financial platforms with stock prices updated in real time, and online gaming platforms. In all of these examples, real-time communication enables the fast exchange of data, which is crucial for effective collaboration and the user experience. Now we will explore some of the ways that real-time communication is implemented. We'll start with a brief overview of Hypertext Transfer Protocol, HTTP. Developed for the World Wide Web, HTTP facilitates the exchange of information between clients such as web browsers, and servers, such as remote machines that host web application logic. The essence of HTTP lies in a request-response cycle, where clients send requests for specific resources and servers respond by delivering the requested data. The first way of implementing real-time that we will discuss is long polling. Long polling is a technique that involves sending HTTP requests at regular intervals to check for server updates. The server delays its response until new data is available or the request times out. Whenever new data is available, it is sent immediately. The drawbacks to long polling is that it demands frequent request response cycles that add to the overall latency, and it can result in unnecessary data transfer when requests are sent to the server even when no updates are available. These drawbacks have led to more modern techniques to implement real-time, like server-sent events, which we will discuss in the next slide. Server-sent events are a technology that facilitates real-time communication between server and client over a single HTTP connection. An initial exchange between the client and the server specifies the intent to establish a server-sent events connection. From that point on, the server can send a response to the client anytime new data is available. The benefit of server-sent events is that they require fewer request response cycles than polling, which reduces latency. However, server-sent events only support unidirectional communication from server to client, which limits their usefulness in applications that require data to be sent from the client in real time. It is this gap that led to the development of the WebSocket protocol as a method of implementing bidirectional real-time communication. WebSocket is a protocol that enables a long-lived and bidirectional connection between a client and a server. WebSockets are established with an initial HTTP request-response exchange, where the client sends an upgrade request to the server, signifying the transition to the WebSocket protocol. If the server supports WebSockets, the connection is upgraded from HTTP to WebSocket. Although WebSocket connections require HTTP to establish an initial connection, HTTP and WebSocket are two separate communication protocols that have distinct characteristics. First, HTTP works in a request-response pattern, while communication over WebSockets is bidirectional. With HTTP, a client sends a request to the server, and the server responds accordingly. WebSockets, on the other hand, maintain a single connection between client and server over which data is transmitted in either direction. HTTP is short-lived, while WebSockets are long-lived. Once an HTTP request is sent to the server and a response is received, the connection is closed. However, WebSocket connections maintain a constant open channel of communication between the client and server. Finally, WebSockets are considered faster than HTTP. HTTP requires initiating a new request-response cycle for each interaction, while WebSockets only require an initial request-response cycle to establish the connection. With fewer request-response cycles, latency is reduced when using WebSockets. Based on our discussion comparing HTTP and WebSockets, we can see that WebSockets have advantages when it comes to implementing real-time communication. These include reduced latency, as well as the ability of data to flow bidirectionally. These advantages, as well as WebSockets adoption by modern web applications such as Slack, GitHub, and Netflix, are what led us to use them in our implementation of Twine. It's important to note that WebSockets also come with their disadvantages. Remember that WebSockets, unlike HTTP, are long-lived. This means that a server maintaining WebSocket connections will require ongoing server resources, such as CPU and memory, to keep these connections open. WebSockets' long-lived nature also opens them up to be particularly sensitive to network disruptions. Additionally, WebSocket, although now supported by all major browsers, is still a newer and distinct protocol from HTTP. Thus, certain environments, such as corporate networks and proxy servers, may block WebSocket connections. Additionally, many existing infrastructures are built, configured, and maintained to accommodate HTTP traffic without considering the requirements of WebSockets. I'll now hand off to Spencer, who will provide a deep dive into the specific challenges of using WebSockets that we set out to solve with Twine.
Thank you, Maddy. First, I will talk about the WebSocket challenges that Twine focused on overcoming. Then I will compare existing WebSocket services and show Twine's place among them. There are two significant challenges with implementing WebSockets. The first challenge is scaling. The long-lived, resource-occupying nature of WebSocket connections causes traffic patterns that are different from regular HTTP traffic, adding new scaling considerations. The second challenge is dropped connections. A dropped connection means the bidirectional flow of data between client and server unintentionally ends. Users experience dropped connections and scaling failures as a service disruption. A service disruption can mean a lost sale, inaccurate financial data, or delayed medical care, depending on the application and how WebSockets were implemented. Twine handles scaling and dropped connections by providing auto-scaling, developer-owned infrastructure with default connection state recovery. Before we show Twine's implementation, we want to lay the groundwork by explaining the scaling and dropped connection challenges and the solutions to those challenges. You may be wondering what scaling means. Scaling is when a piece of infrastructure is upgraded to accommodate higher usage. There are two types of scaling. Vertical scaling is when a single node, like a server, is upgraded with better hardware. Adding more RAM is one example of vertical scaling. This approach is relatively simple and fast to implement. But there are significant downsides. One downside is that vertical scaling one node will eventually reach a limit. Another is that no matter how powerful, a network comprised of a single node will always be a single point of failure for an application. Vertical scaling does not add redundancy. Horizontal scaling, on the other hand, is when the original node is duplicated. Together, multiple nodes form a cluster. If one node goes offline, others remain available to serve users. This enables nearly limitless scaling and redundancy. Each node may be small, but enough of them can together handle any traffic load. The downside is that horizontal scaling adds complexity. For example, traffic must be distributed between the nodes in a cluster. Selecting and implementing the correct distribution algorithm is not always straightforward. Shared state is another layer of complexity. If each node must be able to stand in for another node, that means they must all draw from the same data source. Otherwise, a user with a session on one node would not be recognized by a different node, and they would have to authenticate all over again. We chose to horizontally scale Twine servers and thus mitigate single points of failure in the infrastructure. If you recall from our previous discussion, WebSocket connections are long-lived and continually use server resources. In contrast, server resources are quickly used and then freed up by short-lived HTTP traffic. In addition to maintaining long-lived connections, a server must account for the overhead of new WebSocket connections, which are established with HTTP before being upgraded to the WebSocket protocol. That means a WebSocket server must handle bursts of traffic from new connections and thousands of concurrent connections, 2 traffic patterns instead of 1. Bandwidth usage can also be substantial when sending data to thousands of concurrent WebSocket connections. For these reasons, a node serving primarily HTTP traffic, but also WebSocket traffic, has additional resource usage and scaling considerations. Such a node would have to scale up to accommodate its primary HTTP traffic and the additional WebSocket traffic. This type of scaling is not optimized for either protocol, thus wasting resources and incurring unnecessary costs. Since a server's aggregate WebSocket connections would require more resources than the HTTP connections, such a configuration would be overkill for a primarily HTTP-based application. In the worst-case scenario, the HTTP cluster's auto-scaling triggers do not adequately account for WebSocket traffic, and users experience a service disruption. The challenge of scaling WebSocket connections can be delegated to a real-time service, such as Twine. This real-time service can independently scale to accommodate WebSocket traffic, taking the load of long-lived WebSocket connections off the main application's servers. Then, each server cluster can use hardware and auto-scaling triggers designed for one protocol's traffic load pattern and resource usage. That concludes the section on scaling WebSockets. Next, we will walk through our second challenge, dropped connections, and how to mitigate them. A WebSocket connection can drop for a variety of reasons and result in service disruption. A connection can drop due to passing through a tunnel, roommates hogging internet bandwidth, or server maintenance, for example. When a user drops and reconnects, they establish a new WebSocket connection with the server. A new connection means that, by default, the reconnecting user is treated as brand new. In many cases, a user would have to re-authenticate just to get back to where they were prior to the dropped connection. Connection state recovery mitigates that service disruption by returning a user to the application's context upon reconnection. That means missed data is delivered to the user in the order that it was originally sent, and that the user is returned to the bidirectional data flow that they were in prior to the disconnection. By this point, we have a solid understanding of scaling and dropped connections. Next, we will compare 2 existing services that help developers tackle these challenges and show how Twine fills a service gap. Twine is not the first service to take on WebSocket challenges. Ably stands out as an excellent choice among enterprise solutions. On the open source side, the Socket.io library has helped millions of developers implement WebSockets. Together, Ably and Socket.io provide everything that Twine provides and more. But comparing them side by side shows a service gap that Twine fills. We chose 8 comparison points for Ably, Socket.io, and for Twine. The first 2 points, connection state recovery and auto-scaling, should hopefully sound familiar. Open source was chosen as a comparison point in consideration of projects where cost and transparency are significant concerns. Dedicated infrastructure is an important point because it means the service handles WebSocket traffic instead of the main application's servers. Ownership of the data stored in a WebSocket service can be a major consideration, leading into privacy and accessibility trade-offs. Exactly once delivery is another non-trivial consideration. This refers to a service requiring acknowledgement that a client received published data. If the acknowledgement was not received, the service will keep trying to send the data. Ease of use. Is the service easy to set up and use? How much configuration is required? This is always a factor in choosing which tool to work with. Finally, multiple language support allows more developers and applications to use a WebSocket support service. Let's see how Ably, Socket.io, and Twine compare on these 8 points. An additional point here is that Socket.io is a library that requires developers to implement what they need. For example, Socket.io provides tools for implementing connection state recovery. It does not provide connection state recovery itself. Reviewing the comparison points, we found a service gap between the open source yet labor-intensive Socket.io and enterprise solution Ably, which is extremely reliable but is a paid service and takes control away from developers. Twine fits between the two as an open source, reliable, real-time as a service that gives developers full ownership of their WebSocket code and data. As we can see from these comparisons, Twine does not offer multiple language support or exactly once delivery. Thus, applications written in a language other than JavaScript or those that require exactly once delivery should not consider Twine. Twine was designed for small to medium-sized applications where WebSocket scaling and dropped connections are paramount concerns. That completes our summary of the WebSocket challenges Twine chose to address. I hope that Twine's use case is clear, along with its place among existing WebSocket services. Chris will now take over and show how we built Twine.
Thank you, Spencer. Now we'll go over the steps we took while building Twine, including how we achieved connection state recovery, how we built out Twine's infrastructure, and the design choices and the trade-offs that we made along the way. As a real-time service, one of the first major decisions to make was determining an efficient way to transmit data in real time. Twine's core server design was based on the publish-subscribe messaging model, which is also referred to as the pub-sub model. With pub-sub, data flows through channels called rooms, which act as intermediaries between publishers and subscribers. These rooms typically signify a distinct category of data. For example, stock market updates or messages in a chat room. Clients can inform the pub-sub service that we would like to subscribe to a room. By subscribing to a room, the client is telling the pub-sub service that would like to receive data published to the associated room. When a publisher publishes data to a room, all clients subscribed to that room receive the data in real time. This model enables decoupling, allowing publishers to send data to any room without knowing its subscribers, and subscribers to receive data from multiple rooms without direct connections to publishers. A central pub-sub-hub manages connections between publishers and subscribers, receiving published data and emitting it to all subscribers of the corresponding rooms. Another major design decision we made was for Twine to be a drop-in service. This means that Twine can be included in a web application's existing architecture as a layer between client-facing code and back-end servers. This allows users of the application to benefit from the real-time capabilities Twine provides, without necessitating the application developer to implement that real-time logic themselves. Once Twine has been dropped into the application, its backend servers can publish data to the Twine server via HTTPS, while indicating what rooms they are publishing data to. Twine receives the published data and sends that data to subscribed clients in real time via a WebSocket connection. To achieve this functionality, we started by building Twine as a single Node.js process that provides an API endpoint for publishing data. A web application using Twine would publish data to this API endpoint from their back-end servers, and the Twine server would accept that incoming data and publish it to all subscribed clients. Twine establishes and maintains these WebSocket connections with clients and also implements the pub/sub functionality previously described. To achieve connection state recovery in the event of a dropped WebSocket connection, we knew that we needed a way to store real-time data. With Twine's focus on data integrity, a persistent data store was needed. We opted to deploy Twine using AWS. Therefore, we were looking for a good storage option within the AWS ecosystem. We decided to use DynamoDB for two main reasons. The first being that NoSQL databases provide faster lookup times than relational databases, with DynamoDB offering single millisecond lookup times. And second, DynamoDB's key value structure aligns with Redis, which we were likely going to use as a caching solution, ensuring consistent data storage across both systems. When developing Twine, a key challenge was guaranteeing that subscribed clients consistently received published data, even during temporary connection interruptions. The process of recovering data after a temporary disconnection is called connection state recovery, and the first step in implementing it is determining when this logic should be executed. We only wanted connection state recovery logic to run when a client had disconnected from Twine and was attempting to reconnect, not on their initial connection. So we needed a way to differentiate between an initial connection and a reconnection. This logic was implemented using a randomly generated identifier called a Twine ID that we stored in a cookie on the client that would persist between reconnections. When a client requests a WebSocket connection with the Twine server, Twine takes different actions based on whether it's an initial connection or a reconnect. For initial connections, a fetch request is sent to the Twine server. The server checks if the request includes a cookie containing a valid Twine ID. Since the Twine ID is absent during the initial connection, connection state recovery logic is skipped. Subsequently, the server generates a random ID, assigning it as the Twine ID in the client-side cookie. When a client reconnects to the Twine server following a dropped WebSocket connection, the server checks the client-side cookie for a valid Twine ID. Upon confirming the Twine ID's validity, the connection state recovery logic executes, retrieving and resending all data that was missed during the client's disconnection period. Now that we have determined when to execute connection state recovery logic, we turned our attention to where Twine would retrieve data from during connection state recovery execution. While DynamoDB exhibits fast read and write times, persistent data stores generally introduce latency when compared to faster alternatives, such as a cache. This difference primarily stems from how these storage options store their data. Persistent data stores, such as DynamoDB, store data on disk storage, while data stored in a cache resides in memory, allowing for faster access. We opted to utilize AWS Elasticache for Redis to facilitate deployment, and because Redis employs a key value data structure optimized for rapid data retrieval. Now, if a client reconnects to Twine within 2 minutes of a dropped WebSocket connection, missed data is retrieved from Redis instead of DynamoDB. This short time frame facilitates swift data retrieval in situations like a temporary disconnection from the Twine server due to brief internet outages or loss of cell signal. If the time since the client's last connection exceeds 2 minutes, Twine will retrieve all missed data from DynamoDB and transmit it to the client. Twine offers connection state recovery for up to 24 hours following the client's last disconnect. Since we were working within the AWS ecosystem, our first step in scaling Twine was to deploy our Twine server onto a single EC2 instance. The long-lived nature of WebSockets makes EC2 instances an ideal choice for hosting a Twine server, given their capacity to stay active for extended durations. This aligns well with the persistent nature of WebSockets, which can theoretically remain open indefinitely. Ultimately, we decided that each Twine service deployment will contain 2 EC2 instances by default for 2 main reasons. First, for redundancy, because our primary goal in building Twine is reliability. If one of the EC2 instances were to fail, we would have a backup already in operation. Second, for scalability. We knew eventually that Twine would need to be able to scale horizontally. Adding a second EC2 instance would allow us to test and troubleshoot the scalability of our Twine servers. With 2 EC2 instances deployed, a mechanism to evenly distribute traffic among servers became necessary. Therefore, we added an AWS application load balancer. This addition evenly distributes incoming requests between the deployed EC2 instances. At this stage, we need to address how to make data published from a backend service available to all EC2 instances. Without this logic, data being published to a room would only be published from a single server. This means that only clients connected to that specific server would receive the published data. To ensure all clients receive data for rooms that they are subscribed to, we integrated Socket.io's Redis adapter into our infrastructure, which will be discussed in more detail shortly. Having multiple Twine server instances in our infrastructure does present the potential for inconsistencies and dependency conflicts between instances. Thankfully, this can be remedied using Docker. Docker provides a standardized and isolated container around the Twine server logic and its dependencies, creating an easily reproducible environment. This simplifies the deployment process and reduces the likelihood of runtime issues, making deploying, managing, and maintaining each Twine server easier. By containerizing Twine's server logic in a Docker container, we've achieved consistent runtime for our application and its dependencies, addressing the challenge of maintaining uniformity across independent environments. To improve the ease of use for Twine clients and avoid the need to manually maintain EC2 instances, Twine utilizes Amazon's Elastic Beanstalk, a managed platform as a service that abstracts away the complexities of EC2 maintenance. In addition to automating maintenance, Elastic Beanstalk also automates the deployment of Twine's server instances and application load balancing. The auto-scaling and health monitoring features it provides dynamically adjust to surges in traffic, ensuring Twine is never running too many or too few instances. While this decision involved sacrificing some control over the EC2 instances, the ease of use and automation offered by Elastic Beanstalk outweighed the alternatives, such as Amazon Elastic Container Service. Our final architecture now features Twine's server logic running in a Docker container within EC2 instances deployed and managed by Elastic Beanstalk. I'll now hand things off to Leeya to discuss some of the engineering challenges we encountered while building Twine.
Thank you, Chris. So as Chris said, in this section, I'll be sharing a few of our engineering challenges, specifically storing and securing the Twine ID on the client, load balancing WebSocket connections, synchronizing state, and load testing. One of our earliest engineering challenges was securely storing the Twine ID client side. If you recall from earlier in the presentation, the Twine ID is a randomly generated UUID that is pivotal in distinguishing between an initial connection and a reconnection. To make this logic work, we needed a reliable way to store the Twine ID client-side. Our options were local storage or persistent cookies. Let's weigh the pros and cons. Local storage is modern and performs faster than cookies, but lacks default encryption, which means we'd have to write the logic ourselves. It also requires manual deletion, another piece of logic we'd be responsible for. On the other hand, persistent cookies are slower, but come with a customizable expiration date we could set without any additional logic and enhanced security features in the form of an HTTP-only flag. This flag prevents potential cross-site scripting attacks by blocking client-side scripts from accessing cookie data. Since mitigating the risk of the Twine ID possibly being intercepted by malicious parties and used for session hijacking was paramount for us, we chose persistent cookies. Though slower, they align better with our requirements, providing Twine with a secure and efficient solution for storing the Twine ID client-side. Another challenge we faced had to do with scaling WebSockets to multiple servers, specifically load balancing the WebSocket connections established with Socket.io. While using the AWS Application Load Balancer to distribute traffic across multiple EC2 instances, an issue stemming from the Socket.io library arose. The problem was the process Socket.io uses to establish WebSocket connections when long polling is enabled as a fallback. Now, I know what you're thinking. What do you mean long polling as a fallback? I thought Twine was only about WebSockets. Although our primary connection is WebSockets, we can increase the availability of an application by adding a secondary connection type, a fallback. Here, that's long polling. Suppose a user's WebSocket connection is disrupted. In that case, the client and server will attempt to preserve the connection by downgrading to long polling. Likewise, if a user cannot connect via a WebSocket connection, due to firewalls, for example, a user can still connect via long polling. When an application's availability increases, so does the user experience. Now that we know why Twine uses a fallback, let's see how this decision created an issue. When long polling is enabled as a fallback, Socket.io takes the following actions by default to establish WebSocket connections. The client sends an HTTP request to establish a connection via long polling. In response, a unique ID, called the Socket ID, is generated on the server and sent to the client. A second HTTP request is sent automatically from the client to the server to upgrade the connection to WebSocket. This request must include the Socket ID. If the upgrade is possible, the WebSocket connection is established using the same Socket ID and the long polling connection is closed. Otherwise, the long polling connection remains open. The challenge is that the HTTP request to upgrade must reach the same server that generated the Socket ID. Failure to do so results in the Socket.io error session ID unknown, which leads to a failed connection upgrade and fallback to long polling. By default, there is no logic or guarantee that the application load balancer will send subsequent HTTP requests to the same server. The solution was to enable sticky sessions in the load balancer settings. Now, when the second HTTP request to upgrade the connection is sent, it will go to a specific server, the one that generated the Socket ID. The next engineering challenge we faced also had to do with scaling, and that was synchronizing state across multiple Twine server instances. Now that we could scale up and have more than one Twine server, backend services could publish data to any number of them. Likewise, clients subscribed to the same room could now be connected to different servers as well. And so the question arose, how would other Twine server instances access this data to broadcast it to their connected clients efficiently? Before we answer that question, let's illustrate the problem to better understand it. Suppose there are two clients, Client A and Client B. Both are subscribed to Room C, but are connected to separate Twine server instances, Server A and B. If data is published from backend servers to Server A, for all Room C subscribers, Server B is unaware of this data. Consequently, Client A receives the new data, while client B, connected to server B, remains uninformed despite being subscribed to room C. And so the solution was to implement the Socket.io Redis adapter. This enhancement ensures that when data is received by one Twine server instance, it is also published to Redis using the adapter logic. Redis, in turn, broadcasts this data to all Twine servers, ensuring that all clients receive the intended information regardless of their server connection. The last engineering challenge we'll discuss is load testing. This step was crucial in ensuring the reliability and scalability of Twine. Using artillery, we load tested for two scenarios: the number of concurrent connections Twine could manage and the amount of throughput Twine could handle. In scenario 1, Twine successfully handled ramping up to 96,000 concurrent users over 20 minutes by auto-scaling to 4 servers. In scenario 2, concurrent users were subscribed to the same room, receiving messages published to that room approximately every second. Upon ramping up to 40,000 users over 20 minutes, we noticed 20 to 40% of users connected but failed to receive a single message. After upgrading artillery servers, the failure rate dropped to 2 to 4%. But unfortunately, it still climbed with concurrent connections beyond 6,000. It was only after simplifying the testing logic that we saw a successful test of 48,000 concurrent connections with a 0.7% failure rate. We believe the failed message delivery was caused by an artillery server bottleneck, the load testing configuration, or a combination thereof. Our load testing journey with artillery provided valuable insights into Twine's performance under challenging conditions. While the results of our most recent tests were encouraging, looking ahead, our future work with load testing involves delving deeper into the issues identified, mainly focusing on testing connection state recovery for each virtual user connected to Twine. That concludes our engineering challenges. Now I'll discuss what a developer needs to do in order to use Twine. First, they'll have to deploy Twine using the AWS CLI and CloudFormation. Then import the Twine client library to their front-end code, allowing their client to interact with Twine. And lastly, they'll need to import the Twine server library to their backend code, which will allow them to publish data to Twine. To deploy Twine, a developer will need to take the following steps: create an AWS account and IAM user to configure all necessary permissions, create an AWS CLI profile that will later be used to deploy Twine, register a Route 53 domain that will later be used with the Twine libraries, request a TLS certificate to authenticate their newly created domain, deploy the Twine architecture, specifying the type of EC2 and Elasticache Redis they want to use, and create a DNS record to ensure the load balancer routes users appropriately. Once these steps have been followed, the Twine infrastructure is complete and ready to connect to via the Twine client and server libraries. This approach keeps a developer's sensitive information, like their AWS access and secret keys, private. To get their front-end code interacting with Twine, a developer will need to import the Twine client library, either from the JS Deliver CDN or by downloading the npm package, then create a Twine client library instance using the Twine constructor and their newly created Twine domain name as seen on line 4. Once the instance is created, a connection is established with the Twine server. From here, the developer, using our awesome documentation, can use any of Twine's built-in functions with ease to connect or disconnect a user's WebSocket connection manually, to subscribe or unsubscribe users to a particular room, as well as listen for messages being sent to a specific room, passing in a callback function to handle the data coming from the backend as they see fit. Similarly, to get their backend code interacting with Twine, a developer will need to import the Twine server library, either from JS Deliver CDN or by downloading the npm package, then create a Twine server library instance using the Twine constructor, their newly created Twine domain name, and Twine API key, as seen on line 4. Once the instance is created, messages can be published to the Twine server using the built-in publish method. Now, I'll hand it back over to Maddy, who will discuss our future work and close us out.
Thank you, Leeya. While we are happy with Twine, we recognize that there are some improvements we would like to make to its architecture in the future. Recall from our introduction to real-time communication, we discussed how HTTP and WebSocket are distinct protocols and therefore have different requirements when used in an application's infrastructure. While we accomplished our goal of creating Twine as a drop-in real-time service that takes the maintenance of WebSocket connections off of an application's existing architecture, we can see from this diagram that Twine will still take on some HTTP traffic in the form of requests from backend servers, shown by the pink arrows. To improve Twine's performance, an optimization we could make would be to minimize the amount of HTTP traffic being routed to Twine. The way we would accomplish this would be to use a separate piece of architecture, such as Amazon API Gateway, that would handle incoming HTTP traffic from backend servers. Now, API Gateway, instead of Twine servers, would take on the task of accepting and processing HTTP requests. This would isolate HTTP and WebSocket logic even further, making the system more robust, flexible, and scalable. Another improvement we can make to Twine would be to provide the developer the flexibility to add business logic to data being transmitted from clients to Twine server. Recall that WebSockets enable bidirectional communication from both server to client and client to server. Currently, if a developer wanted to add business logic to process data incoming from clients, they would need to implement this functionality themselves by first routing client data to their application's backend servers for processing, and then to Twine to publish. Thus, we would like to add an in-transit data processing feature to Twine that would allow us, the developer, to dynamically process incoming data from clients to Twine server. This could look like providing serverless functions that the developer could use to apply business logic while the data is in transit. That's all we have. Thank you everyone for listening. We hope that this walkthrough was informative, and we will now open the floor for questions. If you have any questions, please post them in the chat or in the Q&A, and I'll read them out. Okay, I see a couple questions here. Let me just pull that up. How much did we enjoy saying pub sub hub? A lot. Okay. What kind of data is saved when users disconnect? Does this need to be set by the user?
I could take that one. So when users disconnect, I don't believe we're saving any additional information. How we discussed the Twine ID that is created upon the initial connection. That's being stored, as well as like a timestamp associated with that Twine ID that basically signifies the last successful message received by that client. So for like a client, that's what we're storing. And then we're also storing all of the message data. So every message being, or any like data being published is also being stored, both in the Redis cache as well as in Dynamo.
Yeah. So then our next question is, how did you come up with the idea, and what other ideas did you consider? I can go ahead and answer a little bit about our research journey. I guess we fell upon the domain of WebSockets in general. And then we kind of noticed that there was a space for an open source option for a dedicated real-time infrastructure while we're looking at the existing solutions. There were a couple of ideas that we considered other than the real-time infrastructure. Trying to think of some, if anyone else remembers.
Like a completely different project?
Yeah,
I
I
remember,
don't know if we discussed if we thought of anything else in the WebSocket area. What else do you remember, Leeya?
yeah, I just remember us briefly considering like GraphQL backend as a service. I feel like our research with WebSockets kind of led us down this road. So really happy you didn't give up on it, Maddy.
Yeah, we also thought of getting into like data lakes, but we wanted to focus on something that can be used for developers. And WebSockets is used by a lot of different real-time applications. So I'm glad we decided as a group to go that way. And then our next question is, what's been your favorite part of building Twine?
Who wants to go first? I'll go first. Honestly, I feel like just seeing the progression, like what Chris laid out, how he started from just connecting one server and just establishing that WebSocket connection. We were like, yay, we got a connection. And then just building upon that little by little, it was a fascinating experience.
Yeah, I can add to that. I would say it was really cool to all get our hands on, some of the bigger parts of the infrastructure that maybe we didn't have experience with at all in core, mainly AWS, and kind of learning that on the fly and putting all our heads together. Like I remember when we wanted to figure out Elasticache for Redis, it was a hard one, but we all just kind of said whoever can get it connected first. We all like tried on our own, and like whoever could get it connected first. And like while that was difficult to learn a brand new technology, it was like really fun doing that as a group, and feel like I got a ton out of the experience.
Yeah, I'd agree with the team aspect of it. Prior to this, it's mostly been solo work. So figuring out how to work together, and then like once we got that operating smoothly, was like a very rewarding experience, watching everything come together.
I'll tag on to that and say that a big part of it was using AWS extensively for the first time and getting all the different pieces connected, figuring out how the different services worked. It was overwhelming at first, but then incredibly satisfying.
Yeah. Okay, another question. Were there any specific load balancing numbers or metrics you were aiming to hit when you set out to build Twine?
I can take this one. We didn't have any specific numbers. I think we felt that tens of thousands of connections would be very doable, but no specific number. In our research, we did find that there's something like a 65,000 connection limit per server. And when we looked into that more, we found that it has to do with each open WebSocket connection requiring an open file descriptor on the server. And the 65,000 limit comes from that, the number of open file descriptors that can be opened. So, well, we didn't want that to be a bottleneck, is the short answer. So we had to ensure that Twine would auto scale before a single server hit that limit. And we were able to achieve that. So I think that goal pushed us to test for so many concurrent connections and to ensure that the Twine server environment auto scaled smoothly.
Yeah. Okay. If there's no other questions, we will wrap things up. Thank you everyone so much for coming. We really appreciate it.
Thank you.